whole point of the discussions we had about cardiac output was to get, as the name implies, blood out of the heart, right? And where does it go once it leaves the heart? It goes out into the vessels. The whole point of the cardiovascular system is internal transport in the body. In order to do that transport, you need to be able to exchange with things, right? So what we're really looking at here as far as blood flow, right? Blood flows from the heart into arteries, right? Large arteries, smaller arteries, smaller arteries. The smallest arteries are arterioles. Arterioles flow into capillaries. Capillaries are where you do exchange. And I'll get to that in a minute. And then from a capillary, it goes into a small vein, a venule, smaller veins, bigger veins, bigger veins, bigger veins, largest veins, vena cava, back into the heart. So when we talk about distance from the heart, what we're really talking about is this. Right? So even though these are physically attached to the heart, the distance from the pumping structure, right, the distance from the ventricles in the entire circuit is the furthest. So what happens, where's pressure the greatest on here? Pressure's the greatest here. It falls all the way down through here. Honestly, by the time you get right here, the pressure's zero. It's non-existent. Okay? And that's why we need that muscular pump, squeeze the veins. They have valves to try to get blood back to the heart. For reasons that will become clear specifically when we do the respiratory system, in the thoracic cavity, there is a pressure that's less, it's just a few millimeters of mercury less than it is in the abdominal cavity. Okay? And the purpose of that is to help prevent lungs from collapsing. You heard of lungs collapsing, and if a lung collapses, a person can't breathe. So in order to allow for lung inflation, we need to have pressure being kind of less in the thoracic cavity. And we'll talk a lot about the why and the how that happens when we do the respiratory system. But what that means for us as far as blood flow, once we're in the inferior vena cava, as soon as we pass through the diaphragm and get into the thoracic cavity, blood just gets pulled and sucked up into the heart. It's just we call that the respiratory pump. It's due to that negative pressure in the thorax, kind of just pulling blood up. So it's hard to get it back to the vena cava, so we need the muscular pump to do that. But as soon as we get it in the vena cava, the fact that the thorax has less pressure than the abdomen means that the blood will just slowly be sucked up into the atrium. Obviously, anything from the superior vena cava is gravity fed. And so that's not an issue. We don't need pressure there. But it's kind of like you think, if you've ever cut a blood vessel, blood just weeps out, right? It doesn't squirt out, right? So if you cut a vein, which is what you would cut, the blood would just weep out. If we cut an artery, if I cut my carotid artery, I could probably hit Carla with blood from my carotid artery.
For being a good student.
Squirt across the room. Right? That's why, in fact, arteries are deep, is we want to try to protect them from that damage. So high pressure, low pressure, blood will flow from high pressure to low pressure. Now what that means is, what happens in an artery? Transport. That's it. Transport. I should say transport, and then in arterioles, we'll see that we use them to help regulate blood pressure, but it's just transport, really. What happens in a vein? Transport. So transport away from the heart, that's the definition of an artery. Transport to the heart, that's the definition of a vein, right? An efferent vessel, an afferent vessel. Where the physiology occurs is right here. Now, remember the structure of an artery? Had layers, called them tunics, right? 3 layers, right? Middle layer's a muscle layer. So tunica externa or adventitia, right? Then we had tunica media, smooth muscle. Then we had tunica intima, which is the simple squamous epithelium, right? Same is true here, all 3 here as well. Larger lumen, smaller lumen, thinner tunica media, thicker tunica media, but still just transport. What we have in capillaries, though, we don't have those 3 layers, right? It consists of the tunica intima only. So a capillary is just the squamous epithelium. Now that makes sense, right? Because if I need to exchange between blood plasma and interstitial fluid, I can't go through the walls of arteries and veins. So I need these thin walled vessels called capillaries to do it. Now there are structurally three different kinds of capillaries. There's what we call a continuous capillary, and that's where the cells are actually held together. So all of the endothelial cells like this are physically held together, and there's no gaps in them, right? So if we were to look at a continuous capillary, it looks like this. So that's a continuous capillary. Fenestrated capillary, fenestra in Latin means window or opening. So fenestrated capillaries look like this. There's a cell there. There might be one here. There might be one here. But you'll notice that they're leaky in between. So they're not held together really tightly. So they're leaky in between. And sinusoidal capillaries have big gaps in between them, like this. So in terms of permeability, least permeable to most permeable. And the place where we have the sinusoidal capillaries are places where we want to have large amounts of exchange. The liver, the kidney, places like that. Continuous capillaries, minimal exchange. Blood-brain barrier is a classic example here. Many a common structure for a capillary is this fenestrated. So if you look at this, we really have two different ways that exchange can occur at the capillary bed. Exchange can occur through cells, and exchange can occur between cells, right? So change that occurs through the cells is what we call transendothelial, trans across endothelial to endothelium. So the only kind of exchange that we can get in a continuous capillary bed is this kind here, right? Because there's no way to go between the cells. Paracellular is the other kind, and that is the kind of exchange that occurs between cells. So in fenestrated capillaries, you can have transcytosis also, but you also get, in addition to that, the exchange between cells like that. So that's paracellular. Para means next to or adjacent to. Cellular, the cells. Now, the exchange that occurs here is driven by pressure. So it is a pressure gradient that triggers this exchange. And in fact, we call it filtration. Filtration. So filtration is the mechanism by which exchange occurs. And it is pressure driven. And it is exchange between, it's all with extracellular fluid. So it's exchange between interstitial fluid and blood plasma. So that's the filtration between interstitial fluid and blood plasma. And then, of course, once it's in interstitial fluid, then this would exchange with cytoplasm, right? With intracellular fluid. So this is how things move from compartment to compartment, is via this process. Transport over great distances in the cardiovascular system, exchange at capillaries between blood plasma and interstitial fluid by a pressure gradient due to filtration. And then once it's in the interstitial fluid, exchange simply by diffusion, facilitated or simple diffusion, or active transport with the cytoplasm, the intracellular fluid. So that's what we're really looking at. That's the whole point, right, of being able to do this, is to maintain that pressure gradient. So the pressure, right, in order to get a pressure there to create this filtration, you need to have a significant cardiac output, right? You need to get blood out to these tissues, and then the hindrance to that is going to be the resistance. Right? So if cardiac output goes up, blood pressure goes up. If resistance goes up to the flow, blood pressure will go up. And so this is one of the things that we want to look at.